Well, I think this might be the last one, or possibly the second last one for this semester. I can check that if I go and look at the website. But in general, I deal with things 1 week at a time. So I can't tell you if there's another one off the top of my head. I will go check that in a minute. Well, in an hour. So this one is about specific statistical procedures. I want to remind you of the story so far before I start writing things. And I'm mainly going to be writing on the document camera. My notes, actually a better version of my notes. My handwriting's pretty crap. But I do, if I work slowly, I can do a nice one. So there will be a nice one on my website later. This one is about specific stats. So far we've talked about what sort of information you need to choose what stats goes with what. And we had a bit of practice at choosing what stats goes with particular research questions, and the major decisions that you have to make are to do with what kinds of variables are involved, whether numerical or categorical, how many categories the categorical variables have, and whether those categories, in the story of how the data was collected, whether those categories indicated to the researcher that they should collect the outcome more than once, or whether they indicated you should split the subjects into separate groups. So, and given those particular situations, last week there was a handout that said what statistical methods went with those. Well, this one's the other way around. It has commonly mentioned statistical methods in research papers and other places, and it talks about what research goes with them. I'm going to come and take one of the handouts, or all of the rest of them. Okay. And this is what the handout looks like. And what it has is a list of the most common types of statistical tests and what research questions go with them. Okay, because and I will today talk about some of the details of the mechanics of how those things work in terms of the calculations that are involved. But the most important thing to know is what purposes those hypothesis tests or other procedures are designed to achieve. That's the thing you really need to know. Because when you're reading someone else's research, as you need to in your critical appraisal, or any time you're reading someone else's research, if they mention a particular procedure, you need to know whether it matches what their goal was, because that tells you whether it was appropriate. And that's what this one's about. So I'm going to start with the Unpaired T-Test, which is also known as the two-sample T-Test. And the Unpaired T-Test goes with this situation. It has a numerical outcome, and it has a categorical explanatory variable. And the explanatory variable has to have two categories. And that's what it goes with. And those two categories are telling you to split the group of people or petri dishes or rats or whatever it is they are into two groups. So it's saying that there are two separate groups of individuals, subjects in the study, and the outcome is measured once per person. Okay? That numerical outcome there is measured once per person. So in terms of the order of time for that person, there's a moment in time where they are split into their groups, as you think about the way that the data was set up. We have a person and they're following their time. There was a moment when you said, what group? And some other time, it could have even happened before, there is a moment where we say, what's the outcome? So that's my time diagram of what happened in the study. It doesn't the outcome doesn't necessarily have to happen after what group it's in. You can actually, these can actually be at the same moment where you have a single person and you figured out maybe their height and their gender. Those two things didn't necessarily happen at different times in your data. It's just as long as that you've asked what group and what outcome. That's what the t-test is for. And it's supposed to be for normal distributions. But it's usually okay to do it anyway if you've got like more than 30 in each group. But what would really happen is in real research you would say something like, when I analyse the relationship between this and the outcome using an unpaired T-test or a non-parametric method if the normal distribution was a problem, something like that. That's what you'd normally say. But if you just said if you just said it with the unpaired T-test, no one would even bat an eyelid and they wouldn't actually consider it at all. But when you came to do the research, a statistician would try the T-test and would try other things and see which one fit the data best. Okay, that's what it's for. And really that's all I need to say about the T-test. That's what it's designed to achieve. Anytime you have two categories affecting some outcome, that's what a T-test is for. So, right. So the data is set up like this. Because all data is set up like this, and I'm going to do my chili and temperature example because it's what's on my notes, and I'm really not that creative. I used all my creativity to come up with the exam questions. So these are my people. And I've got a group with chili and a group without chili. That's how it will look if you've got an unpaired T-test. You'll have a collection of people with one category and a collection of people with the other category, and they've all got their own temperature. And the way that the test works is that you take each group and you calculate a mean and a standard deviation. And they call the mean X bar or Y bar and a standard deviation. And this one will have a mean and a standard deviation. And then you will combine all those four numbers that you calculated into one T statistic. And if you want to know, it's x1 bar minus x2 bar over the square root of s1 over n. If you really want to know, but you don't, right? But that's a calculation. So the thing is, remember the whole goal of a hypothesis test is to take all your data and by some method produce a single number. And that single number in a t-test is called t, which is why it's called t-test. And it's only called t because they'd already used z and s and x and y, and that was the nearest letter they thought of that hadn't been used for something else already. When Gossett first invented this test, he used a Z, but Z had already been used by other people for something else. You might also need to know that this is sometimes called the student's T-test. So if you ever see the student's T-test, it's the same thing. Because the person who first published this wasn't allowed to publish it under his own name because he was working for the Guinness Beer Company, and all the work that he did there belonged to Guinness, so he published it under the name student. So, and then from the t, we produce a p-value. Because that's the goal of any of these things. The t is only a means to an end. Hypothesis tests, the aim is to get to a p-value. And the way that I get the p-value is I compare my t to all the t's that could have happened. These are all the t's that could have happened, and the more likely ones are in the middle near 0, and I get my t and I mark it there, and I mark the negative version as well, and I colour them both in, and I figure out that area, and that area is the p-value. That's how the p-value is calculated. Of course, in practice, you just chuck it in a computer and it tells you the answer. So, the reason I draw this diagram is so that you can know what it means by two-tailed or one-tailed. See this? This is a tail, like as in tail. So this is a two-tailed test because I've calculated my p-value using both tails. A one-tailed test only uses the tail on the side where your t comes out, because my t might have come out to, 1.8. The two-tailed one uses the minus 1.8 as well. Two-tailed is just to be more conservative. It's harder to come up with a significant effect with a two-tailed test. When I was taught statistics back in the day, I was taught that you should always use two-tailed tests because one-tailed tests are just a little bit dodgy. Because you have to make a predetermined decision as to whether you expected the answer to come up as positive or negative. And sometimes you don't know for sure to begin with. If you knew it was definitely going to be positive to begin with, why are you doing a hypothesis test? Because you already know the answer. And so that's why you're supposed to do two-tailed tests. They're more conservative. So in case you're ever looking at that, that's what it means. And just a little bit of a diagram of how the data is structured. A little bit of a jittered scatter plot. I've got my yes and no for Chile, and I've got my temperature here, and I might have the yes group having a collection of dots here, and the no group having a collection of dots here, and that's the mean for the yes group, and that's the mean for the no group. And just by looking at it, I can tell that they're far apart from each other. And what the T-statistic does is it gives you a standardized measure of how far apart everybody is from everybody else. Okay, taking into account whether the difference is because they're in the same, because they're just different people, or because they're in different groups. And so the t-test here, this will come up with a big T and a low p-value. But the problem is that if we had the same means, but the data was more spread out, it would be much harder, if I hadn't marked those means to begin with, it would be much harder to tell if there really was a difference. Okay, if I lump everybody into one big group, there's a blob here that is the yeses and there's a blob down here that's the no's. But if I lump all these into one big group, they all overlap so much, there's no way of telling whether the yes or the no is any better. And it's not, right? Because this yes is way worse off than this, well, has a much lower temperature than this no. So if there's a greater standard deviation, which is what, greater spread, which is what standard deviation is about, a greater spread will make it harder to perceive differences. Okay? But if you had more data, and it turned out that when you collected more data, it was all concentrated close. Sure, it's really spread out, but it's all concentrated close together on these, then it's easier to tell that there's a difference. Sure, there's some yeses that are way less than most of the no's, but most of the yeses are more than most of the no's. So what I'm getting at, which is the next lecture, which is about sample sizes, is that if you have a wide spread, you need bigger sample size to be able to perceive the difference between the two groups. Okay, there you go. That is my talking about the unpaired T-test. The next test is the paired T-test. So the paired T-test answers the same question that the unpaired T-test answers, but with a different structure to how the data was collected. So in the paired T-test, there's still a categorical explanatory variable and there's still a numerical outcome variable. But this time the categorical variable doesn't tell me to split people into separate groups. It tells me to measure the outcome twice for every person, once under each different situation. Okay? So in the unpaired T-test, the category tells you two different groups. In the paired t-test, the category tells you two different situations and everybody's in both. And in terms of the time order events for my people, I'll measure the outcome under one category, and then later I'll measure the outcome again under another category. Whereas back in the two-sample t-test, I figured out which group they were in and I measured the outcome as separate events. But in the paired t-test, I measured the outcome and what situation they're in simultaneously twice. So the pair is referring to this pair of measurements. Right. And the way the paired t-test works is that the data is structured differently, and so you have to do the calculation differently. You've got a temperature for chili yes, and a temperature for chili no. And everybody's got two measurements. Person number 1 has a temperature for chili yes and a temperature for chili no. Person number 2 has a temperature for chili yes and a temperature for chili no. Person number 3 has a temperature for chili yes and a temperature for chili no, and so on. So what we actually do in the paired t-test is, because we know that these two measurements belong to the same person, we combine them together into one measurement for that person. And what we do is we calculate the difference. We'll put them together and that will do maybe this minus that. And then we'll put them together and that will give me a difference, and you put them together and that will give me a difference. So everybody has a single measurement of the difference between their two previous measurements. And the way that the paired t-test works is that I actually completely forget about the original data and I just work on the differences. And so I have a brand new question now. It goes like this. This person has a measurement on them of the temperature with yes for chili, and a measurement of the temperature with no for chili. I combine them together to get the difference in temperature. And then I imagine this. Every person has only got one measurement on them now, just the difference. And so now my question is not, how does this affect that? Now my question is just, I want to know more about that difference in temperature. I have turned my question about two measurements into a question about one measurement. And I want to know, is the difference 0? Because if chili doesn't make a difference, then there will be no difference. The difference will be 0. Now, some people, it might make it worse. Some people might make it hotter. Some people might make it colder. But on average, it might overall no difference on average, and that's what the question is actually asking. And so I actually now perform a new calculation just on this new data. Okay. So back here, I take these differences, I figure out their mean and their standard deviation, and I do this. And that is my T. This is why the paired t-test is sometimes called the one-sample t-test, because I'm actually imagining this as just one measurement. And that's why it's called the one-sample t-test. So that's the paired and the unpaired t-test. And really that is one of the most difficult things for people to distinguish between in terms of how to choose which one. The purpose of that little discussion just there is that hopefully with more information about the mechanics of how they're calculated, you can have more information about how to distinguish between them. Okay, the next one on my list is Anova. So the AN stands for analysis, the O stands for of, and the VA stands for variance. So analysis of variance, that's what Anova stands for. And Anova actually makes way more sense, like the calculations are harder, but it makes way more sense than the t-test because it matches better to that diagram that I drew. So for me personally, it makes more sense. So the way that Anova works is it's exactly the same situation as the t-test, except that you have more than 2 groups. Okay, that is the situation that analysis of variance is in, and you end up with 3 separate groups, one that goes with each category, and everybody's had their measurement of them taken once. So if you imagine the time order for a single person, at some point you've said which group, and it's one of the 3 options, and then later it's what's the outcome. So the picture of the time order events is exactly the same as it is for the unpaired T-test. It's just that instead of only having 2 options for which group, there's 3, or 4, or 5, or however many there are. Once you get past 5, we're into we probably should be doing regression because our groups are distinguished by numbers probably. So that's what analysis of variance is for. And the picture that goes with it is this. So this is maybe group A and group B and group C. And then they've got their outcomes. Whoops. And the philosophy behind it is this. Each group has a mean of their own. And I'm going to actually go back to the real meaning of what statistics is for, is to analyse why people or things are different. My big question is, if I have 2 random people and they have different outcome, why are they different? Are they different just because people are different, or are they different because they're in different groups? And so what I want to know is how much of the difference is caused by being in different groups, and how much of the difference is just because, well, random stuff that I don't know any more about. So I want to compare the random change to the change between the 2 groups. And that's how I do it. And the way that I do it is I figure out a grand mean, lumping them all together into one big group, and I compare all the group means to the grand mean, and I compare everybody to their group mean. And so we actually do a calculation. And now I do have something on the computer that I forgot that I had made that I will show you. Okay, so here's a diagram. Oh, I did that, yes. Here's a diagram with some dots, and I want to show you this Anova table just here. This is how Anova will be presented when you do a computer. It will produce a little table like this, and it has all these different calculations in it. But the goal I want to point out is that over in the t-test, the test statistic's called a T, and this one it's called an F, just here. And it's called F after Fisher, who invented this test. But the F is really only a means to an end. It's a way of calculating the p-value. So we'll see at the moment that the p-value is 0.02. So my computer has calculated that there is a significant difference, that whatever category is causing my groups to be different is having a significant effect on the outcome. I'm just going to get to show where the means are. So group A has a mean there with the red line, group B has a mean, group C has a mean, and there's the grand mean. And if I move the points, the means will move. So if everybody's bunched close together, look, my p-value went to 0. It's so small my computer rounded it off to 0. But if everybody's spread far apart, even though the means are quite different, it will be harder to tell that they are. Oh wow, I'm going to have to spread them quite far. Look, it's gone up above 0.05. Now the computer can't tell how different they are. And if we look at it, if we lump them all together into one big group, all the blues and yellows and reds would be mixed together and it would be harder to tell. There you go. So in my handwritten notes I will have a description So what you have is these things. This is what the table will look like. And it records all this different information. This SS is the sum of the squared differences between the group and the grand mean. This SS is the sum of the square differences between each individual person and their local group mean. This is the sum of the differences between differences between everybody and the grand mean. And there's all these calculations you do. And so you have that this plus this has to come to this plus this has to come to this. This is to do with how many people there are in each group and how many groups there are. And this divided by this equals this, and this divided by this equals this, and this divided by this equals F. So it's all there just so that you could check technically whether the calculation had been done correctly. And then the F statistic, we look that up in its distribution, which is this shape. And we only do a one-tailed one for the F because it actually is literally impossible for it to be the other side. So there is no such thing as a two-tailed F statistic because mathematically it's impossible. That's the only time you can be sure, because mathematically is completely sure. And so this is the p-value. One thing I do need to point out about Anova is that the Anova there is a difference. It will either say there is a difference or there is no difference. But it won't tell you which group is different to which. It will just tell you that there is a difference somewhere. At least one of the groups is different from at least one of the other groups, but it doesn't tell you which one is which. So the only way to know for sure is to actually just ignore some of the groups. When I go back to my original diagram, Anova will say that one of the groups is different, but it won't say which one. So when you get that p-value at the end that comes under 0.05, that's the statistics declaring to you there's a difference. But if you want to know where it is, you'll have to ignore group C and just compare these two, which is what a t-test is for. And ignore group B and just compare A and C, and that's what a t-test is for. And ignore group A and do B and C, and that's what a t-test is for. You're going to have to compare every group to every other group, or at the very least, everybody to the control. And so that's what's called post hoc t-tests. Okay, so if you ever hear the phrase post hoc t-test, it's just a natural thing that you should do after doing Anova to find out which group is different to which. Of course, if the Anova says there's no difference, you can stop. Because it says all the groups are the same, you can stop now. But if the Anova says there is a difference, you're supposed to continue to try and figure out which group is causing the problem. And they might all be different, okay? Because it's not really a problem, you actually want it to be different. So that's analysis of variance. Okay? How are we doing? All right. The chi-square test. Sometimes called the chi-square test for independence, sometimes called the chi-square test for homogeneity, sometimes called Pearson's chi-square test, all the same thing. So it's technically Pearson's, because Pearson invented it. The chi-square test is designed to answer a question like the t-test, except that the outcome can be a category. And the chi-square test, it doesn't matter how many categories there are here or here, it'll work fine. It's much more likely to come up with a good p-value if you've only got a small number of groups on either end, but it will work just as well if there's 2 here or 3 here or however many. That's the chi-square test. But it's very important that the chi-square test actually only is designed for an unpaired situation. So everybody is in a separate group. These 3 categories is telling me to have separate groups. Okay, so in terms of time and order of events, whoops. It's the same as the way Anova is done. Now, you might not know which of them is the outcome and which of them is the grouping. Doesn't matter, okay? It doesn't matter which way around it is. It will still do the same job even if you've got it backwards. But mostly you can easily figure out which one is causing the change. So obviously if it's the difference between gender and participating in volunteer work, your participation in volunteer work does not change your gender usually. And so it could, conceivably, but usually not. And so normally the grouping is the gender and the outcome is participation in volunteer work. So you can usually figure out which way around it is, but it doesn't matter if you've got it wrong in terms of, it matters for the person reading your research. They'll go, what are you talking about? But for the statistics, it'll come out the same. So the data's the same. As for the unpaired T-test, you'll have a whole group that have yes and a whole group that have no, and then they'll have an outcome. And so you'll take these and you'll figure out some percentages. Actually, you won't do that at all, but I mean, that's what you're aiming for. You'll just take a category and you'll say, all right, based on chili, yes or no, there's maybe a total of 18 people with yes and 18 people with no. You set that up to begin with. And then you go, well, out of the yes people, how many felt hot? And maybe 13 of them felt hot and 4 of them felt no. And out of the no, maybe 5 out of them had said no and 14 out of them said no, feel hot. So this is that's not a B, it's a 13. This is the yes group, there's 13 saying yes for feeling hot and 5 saying no. And this is the no group, there's 4 saying yes for hot and 14 saying no. And then what you do is you go, just a second, if chili didn't make a difference to whether you felt hot, this is really just one big group of people, right? There's nothing to distinguish them because chili doesn't really make a difference. So if chili didn't make a difference at all, then it's really just one big group which has 17 people who felt hot and 19 people who didn't. And I want to know, just if it was one big group, that'd be what the percentages, 17 out of 36 and 36 people in total, and 19 out of 36. If chili didn't make a difference, I'd expect that same fraction to appear here too. So if chili didn't make a difference, I'd expect 17 out of 36, that fraction to be here. So whatever 17 36th of 18, that's what I'd expect to be in this spot. And so you figure out this new table of what you would have expected to happen if chili didn't make a difference. A new table, and then the calculation is this, just in case you're wondering. The sum, that's the Greek letter sigma, which stands for sum in maths. The observed number that I saw in my actual table minus the expected number squared over the expected number, and I add them all up, and that's the chi-squared statistic. Awesome! And Pearson was very, very clever to come up with this idea. Like, it's mind-bogglingly like, what is going on? Why is it a chi-squared? Very clever, okay? But really the philosophy is that you're just trying to compare what you've got to what you would have expected if it was just one big group. And so that's, in my example, it comes out 28.6. Now, if there was no relationship, your observed ones would all be exactly equal to the expected ones. Yes?
Where do you get the expected numbers?
Oh, well, you say this one here in the yes category, if it was the same as the big group, you'd expect 17 out of 36, that percentage of the 18 to be there. That's how you calculate it. I would recommend looking it up in a book, but you've only got 10 minutes to go. But that's the idea behind it. So the observed one and the expected one should be the same if there was no difference between the two groups. If the two groups were exactly equal to each other in terms of how many yeses and nos they had, then it'd all be the same percentage, right? Just under half, 50%. So I would have expected 50% of the yeses to be in this category here, but it's not. It's totally bigger than that. Roughly 50%. And so that means that 0 is the most likely thing to happen if the null hypothesis is true, if there's no difference, and you look it up in the chi-squared diagram and you get a p-value. Now, one thing I do want to say is, while that diagram looks the same as the F diagram, to the naked eye and my bad handwriting, bad drawing, it is mathematically different. Just like the T-test, the T-test diagram looks like a normal distribution, it is subtly different, but we can't tell with the naked eye. But the universe can tell. I should say that you can also do Fisher's exact test. And Fisher's exact test is truly cool because it really matches exactly what you would want. What you actually do with Fisher's exact test is you say, well, if they're all one big group, then whether they had chili or not doesn't make a difference, so why don't I just relabel everyone in a different group and see what happens then? And I do that for all possible arrangements of everybody into the two different groups, and I figure out what the percentages are, and I compare my percentages I got to all the ones that could have happened by rearranging people into the different groups. And when Fisher invented his test, it was before computers, and so Pearson had to come up with something that they could do by hand. Right? Because if you've got like 36 people going through all the possible arrangements, it's going to be really hard. But now we have computers, it only takes a few seconds. And so that's why Fisher's exact test is now a lot more common than it used to be. Fisher actually invented his Fisher's exact test in order to tell if one of his friends was able to by taste alone, tell if the milk was added to the tea before or after the hot water. That was why it was invented to begin with. There's a fabulous book called The Lady Tasting Tea, which is about the history of statistics in the 20th century, and that story's in there. So interestingly, as much as he was a really bad lecturer, Fisher seemed to be quite a fun-loving sort of guy, but he wasn't very good at teaching. Okay. Finally, in the last few minutes, I do want to talk about McNemar's test. So McNemar's test is the same situation as the chi-square test, but the paired. It's the paired chi-square test. No one calls it that. I really wish they did. That would make so much more sense. You've still got... Oh, except for this, McNemar's test only works in the two categories to two categories situation. If you've got more than one category, I believe it's called Cochrane's Q. Could be wrong about that one. It's in the document that I gave you last time. It comes up so rarely when people ask me that I don't know what it's called, so I have to look it up every time. But it's a paired situation. Everybody's got two measurements of the outcome. So in terms of our time order of events, I have the outcome under the category number 1 and the outcome under category number 2, like that. So, McNemar's test is really quite interesting, but you still make a two-way table, but you're counting something completely different. Right. I might leave that there because I want to talk about one more thing before I go. No, maybe not. So I'm just going to say perhaps this is A and B and my outcome is yes and no. So outcome in under category A could be either yes and no. So everybody's been in category A and they had an outcome when they were in category A. Okay, and either they had a yes or a no. And everybody's been in category 2 as well. And they either had an outcome of yes or no. Crap. There we go. They either had an outcome of yes or no. So remember that everybody's got 2. So this person here has a yes for category A and a no for a no yes when they were under category A and a no when they were under category B. So for example, maybe when they had chili, they said yes, they felt hot, and when they didn't have chili, they said no, they didn't feel hot. But some people said yes for both, and some people said no for both. The philosophy of it goes that so category A, maybe category A is yes for chili, and maybe this is no for chili. So maybe, if chili didn't make a difference to your temperature, you would say either yes for both or no for both. Right? Either you always feel hot after a meal, regardless of whether it's got chili in it or not, or you always don't feel hot after a meal, regardless of whether it's got chili in it or not, because the chili doesn't make a difference. Now, there's going to be some random people who just randomly feel hot or not for no good reason, and so there's going to be some people here in the disagree category. They're going to be hot when they didn't have chili and cold when they did, or vice versa. But these people, we don't care about these people because they were the same under both. So they don't tell us anything about whether whether there's a difference, because they're the same. And so what you're interested in is the people here. And you actually make a brand new table. So you have yes in category A, and the yeses, crap. So yes in A, no in B, and no in A, and yes in B. And you make a brand new table which has a total. And if it didn't make a difference and people were just randomly being hot or cold for no good reason, you'd expect it to be 50-50 here. So if they're just randomly being hot or cold for no good reason, then there'd be the same number in both of these, and so you compare what you have to that, and you can do a chi-squared test for that, or it's called the chi-squared test for goodness of fit, or you can do the z-test for 2 proportions, whatever. McNemar's test is the process of getting from here to there. So you do this chi-squared, and you look it up the same way that you do for the ordinary chi-squared test. The thing I just wanted to point out, the real point is this here, that it's the paired chi-squared test. I needed to say this to you so that when you say, oh, it's a two-way table, that doesn't necessarily mean that it's the ordinary chi-squared test. You have to look very closely and see, has the outcome been measured twice for every person? Okay? Right. Now, there is another lecture that will come later that will be on any statistical methods that you want to know about. So between now and then, if there's any you want to know about, let me know, because I didn't get time to talk about logistic regression or the odds ratio. But I will talk about anything you're interested in, especially logistic regression, later. I may even have time to talk about them next week. So I'll pick up where I left off in the next one. Thanks.